So I write compilers every day. I still write compilers every day. I'm sitting here in my spare time between talks writing compilers. So you're getting this from the perspective of a guy who actually writes the compiler. So, which means I'm an engineer, not a marketing guy. I'll say some things that are a little bit out of line, but that's okay. You're getting what I believe is true, not necessarily what the company's going to believe is true, which is what it is. Now, as was mentioned before, PGI was acquired by NVIDIA just a little over a year ago, a year and a quarter ago. So things were a little bit easier when we were independent. Now I'm part of the green machine. I'm talking here about interoperability with CUDA. I'll mention a little bit about interoperability with OpenCL for targets that are OpenCL enabled. It's harder with OpenCL, and I'll mention why that is at the end here. This is my new graphic for the target architecture. I really like this graphic, partly because I designed it, but partly because I can map a lot of different architectures onto this. So obviously this would map very well like a multi-core and say a GPU. And GPU has its memory, high bandwidth. CPU has its memory, high capacity. Everything is high. Now suppose I wanted to say I'm going to look at the Knights Landing, the self-hosting thing. Throw this out. That's my Knights Landing, near memory, far memory. Suppose I want to look at the AMD APU. So the APU is CPU cores and GPU cores on a chip sharing the memory interface to memory. You throw that out. You've got your high-speed cores, your high-bandwidth cores, all sharing one path to the same memory. So this is my universal picture for all computer architectures for the next 5 or 10 years. This is what we have to target. And I'm not addressing, I'm just doing the node problem, not the PGAS or the MPI problem, obviously. So, okay, I'm going to start this with a couple of CUDA examples, just because I'm talking about interoperability with CUDA. So in this case, each example here is over 2 slides. This one is the program, the compute part. So a atypical, not necessarily every, but atypical CUDA kernel routine. You compute your index from your location in the grid in the block. This is the index of the array, to the index of the iteration set I'm going to work on, and then I go do my work. And then around that, you've got the host doing things, the memory management, and then launching the computation. Now, I'm just going to mention very briefly CUDA managed memory. If it works, will remove most of the memory management overhead, changes other things. With the AMD APU, they will get into the same situation where they're using OpenCL, but they'll have this a shared memory interface where they can use the same addresses on the host part, the CPU part, and the GPU part. Although, to my knowledge, that's not yet available. They're still working on their software. The hardware is available, the software is not, to my knowledge. You can use CUDA in Fortran. So CUDA Fortran, it's just CUDA in Fortran. And my argument is if you're a Fortran programmer and you want to program CUDA, this is your solution. If you're a C programmer and you want to program CUDA, don't use this, because it's not going to solve any problems that you don't already have. But Fortran is a higher level language than C. I'll argue that to my death. And so there are some advantages to Fortran. The kernel code looks very much the same. You find your index and you do some work on the index. The host code for CUDA Fortran has some advantages, like you can add, we have keywords for device data. You have a device array, you just use an allocate statement, it allocates it. You do an array assignment, well, if it's host to device, it'll do an array assignment to the device. So there are some advantages to having a higher level language, and you can do some of that. And again, CUDA Fortran has the managed attribute. Instead of the device attribute, you could change that to managed, and then allocate it in managed memory, and then the CUDA memory manager would manage the data traffic for you in some sense. And we've seen examples of OpenACC. So what do you have with OpenACC? Well, you've got data management, you've got computation management. Right? Data management with data constructs and data regions, and computation management with parallel loops, which basically turns into a kernel launch of some kind. So it's the same operations, they're spelled differently, but you're doing the same sort of thing in both types of ways to do it. The Cray and the PGI compilers for the NVIDIA targets are built on top of CUDA. PGI has a compiler for the AMD GPU as well. It's built on top of OpenCL. We'll talk about that again at the end. But okay, on the ones that are built on top of CUDA, can you interoperate? Because, as John mentioned, compilers don't do everything for you. Sometimes you have to dive into a lower level, be it directly with CUDA or some other tool. And so I was asked to present this, and that's what I'm going to do here. So I'm going to show a couple of different aspects of interoperability. So in the middle of, say, I don't know what I'm supposed to be showing here. Oh, this is, why is that different than this?
One's Fortran and one's C.
Oh, okay. Looks the same to me. All right, so how do I manage? Okay, so here's two obvious things you can do. One of them is, if I'm in the middle of a CUDA program and I want to do some OpenACC, I just want to do a loop. Say in particular, now with CUDA, if I want to launch a kernel, then you've got to extract that thing to a routine and then do a launch and syntax. With OpenACC, just put a directive in front of the loop. And if it's not a computationally intensive loop, how much overhead do I have to do to get this on the device? Or as someone mentioned, I think John mentioned earlier, if it's a reduction, it's doubly hard because now you have to do 2 kernel launches to get it down to a scalar value for reasons of problems with the reduction. Well, I guess it depends on how clever you are, but in many cases, we do 2 kernels to get down to a single reduction. So in the middle of a CUDA program, can I just use an OpenACC loop to do something trivial? And the answer is yes. So this is basically, from the point of view of OpenACC, I'm managing all the data with CUDA. I'm just doing some computation with OpenACC, and I do that by device pointer. This is one of the data clauses of OpenACC. Tells the compiler, this value is already on the device. That's actually the device pointer. So just use that pointer on the device. Now, clearly, you better have a device, or this isn't going to work, but if you didn't have a device, that wouldn't work either. So you're golden. And it works just as well in Fortran. I can tell the difference this time. So in CUDA Fortran, you can have the device attribute. Now, in CUDA Fortran, there's only one implementation, to my knowledge, today as PGI. So we play a little fast and loose with the interoperability between CUDA Fortran and OpenACC, since it's our compiler that does both. So, for instance, OpenACC understands the device attribute. It says, oh, you're doing something here, it's on the device, so when I generate code for the device, I don't need to transfer any data because it's already on the device, so it understands it. And this becomes part of the interface to this subroutine. So if this were in a module, say, it would say, okay, when I call this, that actual argument had better have a device attribute because the dummy argument has a device attribute. It becomes part of you have type, kind, rank, and device attribute. It becomes another one of those features. Okay, fine. So you can use a device pointer, or for CUDA Fortran, you can use a device attribute, or if you're in Fortran and you don't want to be so evil, you could just add device pointer for dummy arguments. So this works in Fortran for dummy arguments, and these are actually passed by reference, and so this is saying the reference argument that's coming in is actually a device reference, so don't do any translation in that device. So the first level of interoperability is you're doing CUDA data management and OpenACC computation. It's relatively easy, and where we find this useful is if you're doing some big program and you just have some little loop, you're going to scale some array, or you're going to reduce something, what have you, then, all right, I'll just do that with a directive, and I'll spend my time, your time is more expensive than computer time, I'll spend my time working on the computationally intensive part. All right, second part. Let's turn that around. I'm in the middle of an OpenACC program, and I want to call a CUDA kernel. And that's equally useful and equally common for that matter, because my compiler the compiler I'm using is crap, can't get any performance out of this thing, or it's not using the caches or the shared memory or the texture memory, or I need to use an algorithm that I can't express in loops, or I'm calling a library routine that this guy wrote and did a really good job optimizing. I don't know who he is, but you could write a library routine that I want to call. And he did a good job optimizing it, so I'm going to call his library routine on the device. So anyway, you can see where I'm going. How do I do that? And you saw a little bit of that already. So, but there's a couple ways. So I'm in the middle of my OpenACC program. I've got the data on the device. Now, John mentioned this a little bit. When you have the data on the device, there's going to actually, with these CUDA devices, typically be two copies, the host copy and the device copy. And there's a table the compiler and the runtime manage to do the translation between this address over here and that address over there. And there's a coherence problem, which becomes your problem because we can't manage it, because we don't have hardware support to manage coherence between the two copies. Okay, fine. So there's an API call. So give me the device pointer for this array, for this address. Does a table lookup and returns the value of the device, and you can use that to launch your kernel. And that works great. That's just that's a C-only thing, unfortunately. Another way, which John already mentioned as well, was the host data, which says for this call, do the table lookup. So now the compiler is going to insert the code to do the table lookup and replace these addresses with the device addresses to pass into this routine that then does the launch. And the reason I have these as separate routines is because you're compiling this part with an OpenACC compiler and this part with NVCC. And never the twain shall meet. And now with CUDA Fortran, things, well, now the CUDA compiler is the OpenACC compiler if you're using the PGI implementation. And if you're not, I'd like to know which CUDA Fortran compiler you are using. You didn't know about this, but on here you can have the host data use device right around the launch, and the compiler will understand that, oh, here you mean launch. Use the device address for that kernel launch, and this is an undocumented feature, but it also works because because the interface to this kernel will have the device attribute on its arguments, because it's a kernel subroutine. Even if you don't put the device attribute, it implicitly has a device attribute on the arguments. So the compiler knows, I need a device pointer here. I need this to be a device address. And A and B are not device arrays. But in a present region, I know that it's on the device, so I know I can get the device. So it will do so. But it has to actually be in an explicit data a data construct, an explicit data construct with a clause for those arrays.
Does it have to be lexically inside the?
Yes, it has to be in the construct itself. So the difference between this is a data construct, this is inside that data region, but the construct is the lexical construct. That's the same terminology OpenMP uses, construct and region. Okay, that's 3 parts. We had the CUDA data, OpenACC computation, OpenACC data, CUDA computation. That's only 2 parts. Now, third part is, what if I need to manage the data explicitly, but I want to put that into that translation table between CUDA and OpenACC? It's not particularly common, but in case you need to do it, I'll just mention it can be done. So we call that the present table. I think John mentioned that also. But there's it's this translation from the host side to the present side. Just maintains the correspondence between the two. And there's an API call to say, this is the host address, this is the device address, this is the number of bytes, and put this in your table. Why do you want to do that? Well, if you're, in some cases, you might want to micromanage the data allocation and to use the same data on the device for different pieces of host arrays. I got this piece over here. Now it's going to point out to the first couple of columns, and the second couple of columns, the third couple of columns. I don't want to go around a loop and reallocate, deallocate, reallocate. I just want to allocate it once, and I'll keep it where it is, and I'll just map it, and there's an unmap as well. You want those things to match up. You're mucking about with tables in the runtime, so tread carefully. Right now, there's only a C interface. We don't have a nice Fortran interface for various not stupid reasons. And then when it comes in here, that data would be present on the device, and that would work just fine. So far. And another interesting one is calling CUDA routines from OpenACC. And so this is where in the middle of my device code, I'm going to call a routine that was, well, you already actually do a lot of that because all the transcendentals are really built-ins that are compiled on the device, but they don't really count because they're all math binary functions. What if there's a function you wrote you want to compile? So until OpenACC 2.0 came out last year, we really didn't have any support for that because these devices didn't have a linker. So you couldn't even link the things together. But now you can. And so the interface of this, so here I've got this this is a CUDA description of with the device keyword that says this is a routine that will be called on the device itself, which is separate from a kernel routine. Kernel routine is launched from the host. Device routine is called from a kernel routine or another device. And I want to do is inside here call that kernel routine. So what I do is I declare the interface. So this part matches that part. I declare it with ACC routine that says that routine is available on the device. So when I call it, I can call it on the device, and it will have that name, and that'll get resolved by the linker, the way linkers resolve things. And then there's this SEQ. SEQ is for sequential. So that's the parallelism clause, and that's to tell the compiler what parallelism is being exploited inside that routine. Inside the routine. And the normal case is the routine has no parallelism. It's just going to do basically one CUDA thread. And so if there's no sync threads in here and no shared memory usage in here, then that should be SEQ. Because it's just, from the point of view of the compiler, that's just a sequential routine, and we'll launch it and call it, and it'll get linked and it will run. It'll be great. And in Fortran, you can do the same thing. I can call a CUDA C routine by giving it an interface block. Bind C tells the compiler use the C binding, which means don't decorate the name the way you would normally decorate a Fortran name. It also means, you also want it for scalar arguments, use the value attribute. Fortran passes by reference, even scalars. Value attribute is something new, relatively new in Fortran. New means 10 years old, but relatively new. It says passes by value. Arrays get passed by references normally. And then can be called in Fortran, inside of Fortran OpenACC loop as normal. If you're using CUDA Fortran, with OpenACC, well, this would have a device attribute, and the PGI Fortran compiler understands the CUDA Fortran device attribute, and so it would have that interface implicit already. Now, I mentioned a bit about parallelism in the device. And why is that important? And people will ask, that's something I never had to think about with OpenMP. Why do I have to think about it here? And the truth is, well, you kind of did have to think about it with OpenMP. So let's go back to OpenMP 3, which basically just parallel loops. You can have a parallel loop, and you can just call a routine, and you just call it a routine. Why do I have to think about it? I don't have to decorate the routine at all. Why do I need to decorate the routine here? Well, with OpenMP A, you only had one instruction set. So you don't have to tell it to generate code for a device so that there will be code available for the device. And B, with OpenMP 3, you only had one level of parallelism. And so either the parallelism was in the code around the routine or the parallelism is in the routine. And if the parallelism is in the routine, then it's your job to make sure all the threads call that routine. There's no checking done by the compiler or the runtime. Is that a common OpenMP error? It used to be. Less common now. Those guys have been trained. Now for the device, we want to tell the compiler that there will be a device version here, and the call actually has a different shape, it's a different implementation, whether it's just one CUDA thread making the call or a bunch of CUDA threads, basically the whole thread block making the call, because they all need to be there all at once. The compiler needs to know that because it needs to make sure that they all get to that point. And I'm not going to go into a lot of details here. I'd be willing to go into as much detail as you want to over an appropriate beverage. But the point being that if you're writing a CUDA routine that you want to call from an OpenACC region that has things like sync threads or uses shared memory, communicates between threads, basically it's a thread block parallel routine, then you want this to communicate across all instances across the whole thread block, then you need to decorate that with ACC worker, not sequential. Why worker instead of vector? Well, because the way it's implemented with PGI and I believe Cray is there's the 3 levels of parallelism, vector, worker, gang. And the worker is the whole thread block. Vector would be one dimension of the thread block. You want the whole thread. More detail than some of you want to know. And the last little bit is handle. So it's built on top of it's built on top of CUDA. So there's things like device handle. Well, the device handle is just a device number. But there's a context handle. There's a stream handles. There are all these different handles that you can get from that are used inside the OpenACC runtime. And you can get those handles if you need to. The interesting one is the stream handle because you're using some CUDA stuff and you want to put things on the same stream that the OpenACC runtime is putting on a certain stream. You say, well, I'm going to get the stream corresponding to this async value, and then I can launch my own kernels or do my own data transfers on that same stream, for instance. Okay. So, all that being said, that's almost the end of the talk here. I only have one more slide, and it's not a thank you slide. I have a vendetta against thank you slides, which I'll be glad also to get into an appropriate beverage. So with OpenCL, now I only was talking about CUDA here. We do have a product for the AMD GPU, which is built on top of OpenCL, and almost none of this works. This slide doesn't. There's an appropriate get current OpenCL device, get current OpenCL queue, command queue, get command queue, get current OpenCL context. But almost nothing else works because with OpenCL, all that other stuff, you're dealing with addresses, memory addresses, a device pointer. What's the memory address? You want to allocate something. What's the address that you're going to use to correspond to the host data, the device data, and so on. OpenCL doesn't deal with addresses. It deals with buffer handles. So, well, just give me the buffer handle. But what do you do with a buffer handle? You can't do address arithmetic on a buffer handle. What if the address you want is in the middle of the buffer? It's a mess. What if I want to write an OpenCL program, an OpenCL subroutine, and link that in with my OpenACC program? Linker? Linker? Who speak of you of linker? Okay. OpenCL 2.0 will solve some of these problems, or maybe all of them. I haven't investigated. We've not gone through the investigation for the complete OpenCL 2.0. We've done no experimenting with OpenCL 2.0. With OpenCL 1.2, which is the one that most implementations have today, none of that stuff, they don't even have that vocabulary. When they do, the interoperability should work just as well. That's as far as I need to go. And so there's my summary. And I'm glad to entertain any questions even without the beverage.
Certainly don't have time for the beverage, but we have time for one or two questions.
There's some websites that you'll have in there. Copies of the
So how much of this is public already? Or?
It's all public. Yeah, it's all. Most of the stuff is actually in the specification. The CUDA Fortran, the implementation part is not. Okay, thanks very much.